This is MEI Statistics Minor, Discrete Random Variables 3, Binomial Distribution. This is video 3.2, Mean and Variance of a Binomial Distribution. Now in A-level maths, we use the property that the expected value, otherwise known as the mean, of a binomial distribution is NP, the number of trials, times the probability of success. But where did this come from? It's one of those unfortunate examples of where you're being blindly asked to trust the teacher. We can have a look in a simulation in Excel. So here we have an input for n and an input for p. Then what I've done is I've used the binomial function to produce a sample of 10,000 individual instances of that binomial distribution. What I've then done is I've counted up for each of the values of x, the frequency, so you can see these numbers will all add up to 10,000, and the relative frequency, which is what I get when I divide by 10,000, and that is my experimental probability. I've then sketched the shape of the function over on this graph, and I've calculated the mean and variance from my simulation. Okay, so I'm starting with n equals 10, p equals 0.5, and you can see my mean is approximately 5 and approximately 2.5. If I F9 and simulate some new values, you can see that the mean is buzzing around 5 and the variance is buzzing around 2.5. So I'll record those results there. If I now change the probability to be 0.1, I get some different values. You can see now that the mean is somewhere near 1 and the variance is somewhere near 0.9. If I then increase the value of n, so there's more trials, and put the probability back to 0.5, we can see now that the mean is approximately 10, the variance is approximately 5, sometimes it's a bit above, sometimes it's a bit below, experimental error. And finally, if I keep n at 20 and make the probability 0.1 now, we can see that the mean is approximately 2, the variance is approximately 1.8. So if you have a look at these numbers, it is quite clear that the mean 10 times 0.5, the mean is approximately NP in each case. Approximately NP, approximately NP. What's happening with the variance? Well, if we multiply this mean by another 0.5, we're going to get to the variance, again with this one. With this one though, it's slightly different because we're multiplying it by 0.9 in each case. So surely we have to consider 1 minus p. So the variance our simulation would suggest is NP, the mean, times 1 minus p. Now, a simulation is a good way of trying to spot a pattern. But if we take a more algebraic, rigorous approach, remember that the binomial is the sum of n Bernoulli distributions. Okay, and a Bernoulli distribution has that probability mass function. The probability that x is 1 is p, a success. Probability that x is 0 is 1 minus p, that is considered a failure. So the expected value of x is going to be equal to the sum of x times the probability that x equals x. So we can use the probability mass function to consider each individual value of x. So when x is 1, that'll be 1 times p. When x is 0, that'll be 0 times 1 minus p. And no other possibilities, so that is simply going to be p. So if y is a binomial distribution, we know that y is the sum of n independent Bernoulli distributions. So the expected value of y from video 1.5 is going to be the expected value of x1 plus the expected value of x2 plus the expected value of x3 all the way up to the expected value of xn. Now, since they are each Bernoulli distributions, they are all distributed exactly the same. So that's the expected value of x plus the expected value of x plus the expected value of x. That's going to happen n times, so we're going to have n times the expected value of x. We've already established that the expected value of x is p, so that is np, which confirms our simulation's findings. Now, for a Bernoulli distribution, we can also calculate the variance, because the variance is going to be the sum of x squared times the probability that x equals x minus the expected value of x squared. So that first part is going to be 1 squared times p plus 0 squared times 1 minus p minus, we already established that the expected value of x is p, so that will be minus p squared. So we're going to have 1 squared times p is p, 0 squared times anything is 0, so we're going to have p minus p squared, which is p times 1 minus p, which is pq. So if y is a binomial distribution, again it's going to be the sum of n independent Bernoulli distributions. So the variance of y, again from video 1.5, is going to be the variance of x1 plus the variance of x2 all the way up to the variance of xn. Since they are all distributed the same, that's going to be the variance of x plus the variance of x plus up to the variance of x. That's going to happen n times, so it's going to be n times the variance of x. We established that the variance of x is pq, so it's going to be npq. So, if y is distributed binomially with n trials and p probability of success, then the expected value of y is np, and the variance of y is npq, or np 1 minus p. Note that the mean is in the formula book, but the variance is not, so you should know those formulae. You can use those if they are known, although you may be asked to prove them in particular cases. So for the first example, x is distributed binomially, so n is equal to 12, probability of success is 0.4, expected value of x is np, so that is 12 times 0.4, which is 4.8. Variance of x is equal to npq, which is 12 times 0.4 times 0.6, which is 2.88. Alternatively, you can simply multiply e of x by q. Find the mode of x. Now, mode is the most likely value, so we need a bit of technology for part 2. We can do it in GeoGebra. We'd get a graph that looks a bit like this, along with associated probabilities here. You can similarly do the same thing on your calculator to get a table of probabilities. We simply look down the list to find the greatest, most likely value. There it is there. So probability that x equals 5 is greatest. So the mode equals 5. Another way round is you might get told the expected value and the variance, and you need to find n and p. Well, that's quite simple too. Because we know the expected value is 6, that means that np is equal to 6. I'm going to label that equation 1. The variance of x is 4. That means that npq is equal to 4. I'll label that equation 2. You can see there's a lot of similarities between the two equations. I would suggest the quickest way to do it is to do equation 2 divided by equation 1. So the NP's will cancel and we'll get Q equals 4 over 6, which is 2/3. Now we know that Q is equal to 1 minus P, so 1 minus P is 2/3, which means that P is equal to 1/3. Sub it into equation 1, we get n equals 18. In the final video, we are going to be looking at Poisson approximation to the binomial.